So for defending against format string attacks, like I mentioned, it's a bounds checking error on the arguments to things like printf that have variable length arguments. As the function ends up reading a certain number of arguments based on the contents of the first argument. So if an attacker can control the input to that first argument, they can control how far up and down the stack that function ends up reading. Certain of the format commands of printf allow it to write back certain things into memory based on one of these arguments. So combining all of that, in certain cases, you can get this read-write, random read-write I/O throughout the memory space. So the defense here, we found some work from SUNY Stony Brook that essentially does a bounds checking on that set of arguments. Go through here. So how it works is it can, based on how the stack pointer and base pointer gets modified as a function executes, and how we know that arguments for a function call end up being placed on a stack. So we can determine from the stack pointer anything below that to where the next function starts are going to be the arguments to that function. So what we do is take advantage of the hardware debugging flags built into the x86 architecture, make a second copy of the function arguments with a canary value placed in front of them. We set a hardware debug flag on that canary, so if ever code reads that, it'll cause a trap back into debug mode. The only thing that would, or no legitimate code would ever read far enough to hit that canary, but printf format string attack would try to read further up the stack than it should be, given that it should only have one argument. And for general memory errors, heap-based errors, a lot of these are due to the fact that the execution heap for most C libraries, the memory allocator, is quite predictable. Mostly they use linked list or doubly linked list implementation. The metadata for the size and the size of each allocated object, what objects are free, is kept in line with the data itself. So if an overflow allows you to overwrite an object, you can also affect the metadata that the stack allocator relies upon. And also because it's optimizing for memory efficiency, trying to pack as many objects into the least amount of space, it ends up being fairly predictable about where in memory an object's going to get allocated. So an attacker can predict with pretty good accuracy that given some object, they can overflow into adjacent objects. So the defense here is to use a randomizing memory allocator, sacrifice some space efficiency for more defense. So first we move all the metadata outside of the heap. There's no good reason why it should be in line with the actual user data, just inviting trouble. So in the way this allocator works, it's the die-hard memory allocator, breaks up the heap into a variety of fixed blocks of different sizes. When an allocation request comes in, picks a block of the appropriate size randomly from its pool of available blocks. So every time an allocation comes in, it'll be directed to a different piece of memory. So now an attacker has no way of knowing that if they overflow object 2 by a certain amount, that they'll end up within object 3, overwrite stack metadata or the heap metadata in a certain way. So every time, for every different instance of a program, the overflow will act differently. The object will be in a different place. So that's roughly well, pretty much the overview of the project so far. We're also exploring some additional things to do in the future. Like I said, there's a very definite limits to what we can do with binary analysis, especially static analysis. You can only get so much information. Heavily optimized or obfuscated binaries, anything from commercial companies that's had packing or anti-reverse engineering kinds of tools applied to it, break all of our binary analysis techniques. So what we're hoping to do in the future is, given the success we had working with Java bytecode, look at similar types of more expressive instruction sets for kind of C, C++ programs. One we're particularly interested in is the LLVM compiler, low-level virtual machine. Uses a typed assembly language in a way as a internal representation throughout the compiler. Can also be treated as a bytecode in the same way as Java would be run through a just-in-time compiler virtual machine, in the same way that those higher-level bytecode languages give us lots more capabilities for analyzing code, determining what it is, where data structures are allocated, and make it very easy to transform code to get these kinds of randomization, statistically based defenses. So, thank you. Do you have any questions? Done? All right, thank you.